Good morning, everyone, and thank you for joining us for today's CISOP webinar. We're excited to have you here as we explore the topic of design of timber connections. Our speaker today is Professor Pierre Quenneville. Pierre has been in academia and in the timber research space since 1988, with specific interest in timber connections. Pierre has been a professor of timber design in the Civil and Environmental Engineering Department at the University of Auckland since 2007. Of course, we encourage you to ask questions, and then this will be read by Jenny at the end of the presentation. Without further ado, I leave you with Professor Pierre Quenneville.
Thank you, Julio. Good day, everyone. It's an honor to be asked to present on that topic, very dear to me. And over the years, I've experienced different levels of blank eyes, blank faces, blank expressions in front of me when I try to explain connection concepts. Practical connection concepts. And when Jenny approached me and I had the idea of explaining more on the load paths that is involved in connection design. And hopefully some of the examples will be basic, but hopefully some of them will be enlightening for you. So I will cover some of the basics of connection design, just an overview of what I'll be talking about in the examples. There are 4 examples, and they're all different in terms of what they involve in terms of timber behavior, connection failures, and steel design. So, starting with the basics. I say to all my students that you cannot design timber connections if you don't know steel design. So, to do a connection design, one will have to know about timber behavior. We'll have to know about timber connection failure modes, and we'll need to know about steel design in various aspects. If we start with the timber behavior basics, we have compression parallel to grain, and the example shown here is where for this load, compression parallel to grain is governing, and it's very basic. There's nothing more to it. The next one would be compression perpendicular to grain, where knowledge of the resistance is primordial, very important, because it will govern the design aspect of that type of connections. Then there will be, for some special cases, the combination of compression parallel and perpendicular to grain, and where the knowledge of the Atkinson formula will be required to get the connection resistance. Obviously, if we mention compression, there'll be tension. So tension parallel in the vertical member, and tension perpendicular to grain in the horizontal members. When we look at the basics of connection failure modes, we have the ductile failures, and these are covered very well with the European model, which is in the new 1720.1 design standard. We also have the brittle failures, the net tension, which we always had, the groove tear out, the row shear, the splitting, and to the right, the block tear out for partially penetrating fasteners in our wood members. But our connections will sometimes have different portions of steel bracketry involved. And the moment that there is a steel bracket and it's not a proprietary connector, then we will be involved in designing plates and bending, compression, tension, or shear. We'll have to check some of the bolted connections in bearing, in shear and tensile. And we'll also have to look at welds. So the design of a timber connection will always include different quantity of timber resistance, timber connection failure, and steel bracket design relative to each other. For some, it will be mostly steel. For others, it will mostly timber connection failure. And I will show 4 different examples, if we have time, where the different quantity of timber behavior, steel design, and connection failures are involved. Always looking at the load path. Well, the first one is an inch connection between beams, and this one involves mostly steel design. So it's a practical example that I show at my students. Tennis center that I visited in Sweden. The plan view is where you have 4 tennis courts. The perimeter walls are light timber framing, and there's 3 main glulam beams supporting the roof. The cross section of the building is as shown. So you have the main glulam beams, and then some supports, glulam columns, and then at the right end, it'll be the light timber framing that will support the glulam beam. So we see this in this photo. We have a suspended beam on the right and a supporting beam on the left. And we see the supported beam being resting on the first column, and to the left there will be another column, but working in tension. For each of these beam location, we have 2 beams. So the joists are supported by, the roof joists are supported by these beams. And here we see a different view, and we see that each beam is composed of 2 laminations. And the connection here, circled, is the one that we will be looking at. So we see 2 plates, a plate at the bottom right, at the bottom of the right beam, and a plate at the top of the supporting beam. So the system is very simple. We have a supporting beam, simply supported with overhang to the right. And then the beam to the right is a supported beam, simply supported. Very simple. The connection between the 2 is hinged, even though we have these tight-fitting dowels. But we see steel plates at the top left and bottom right of the connection. This is what we see. See the bottom plate supporting the supported beam, and the plate at the top of the supporting beam. But what we don't see is that there's a steel bracket between the 2 beam laminations. And this steel bracket is composed of three plates with welds. So quite simple in terms of transferring the loads. And the load paths, when we have to design this connection, involve 7 different steps. So we have first the right beams supported by the steel plate and bearing, and that involves wood compression perpendicular to grain. So when we look at the system, we have our supported beam, and it is resting on the bottom of the bracket. The length of this of the bearing plate needs to be designed such that there's no bearing failure in compression perpendicular to grain. So the force is applied. We know the reaction from our beam analysis, and taking our compression perp to grain resistance. The length of the steel plate is the only unknown. W1 is the width of each lamination. And at this point, we would have assumed that, or we have taken the decision that the plate would be as wide as the 2 laminations. So once we know the length, we need to determine the thickness of that steel plate. The beam or the plate is designed as 2 cantilever beams. There'll be a point of symmetry in the center. Our moment at the shown on the right diagram is just our W1 times the length of our cantilever square divided by 2. And this has to be smaller than the resisting moment in our steel plate. Using the section modulus of our steel plate, we have the length of the plate and the thickness of the plate square divided by 6. And we use NZS 3404 to determine this. The next step would be to design the welds between the bottom plate and the vertical plate. And then the next step would be to come up with the design of the vertical steel plate in tension. So at this point, we would have decided that the vertical plate is as wide as the length of our, or wide enough to cover the entire length of our top and bottom steel plates. We know the tension force. It's then the reaction divided by the cos of the angle. And at this point, the only unknown is the thickness of the plate. And we just need to make sure that our tensile resistance is as high or greater than the tensile force. The next 3-step, which constitute the weld between the top steel plate and the vertical steel plate, the top steel plate and bending, and the left beam supporting the steel plate and bearing, which again is wood compression perpendicular to grain. These steps are equivalent to steps 3, 1, respectively, if the beam grade is the same, or the beam bearing or compression perp to grain of the 2 beams are the same. So we don't have to replicate the design. The design would be the same at that point. That's what we would have. We would just replicate the load of the from the top plate to the top of our supporting beam. So that example was one very simple connection, but mostly involving steel. The next one is different ones, timber to timber connection. And in this one, it's mostly timber connection failures that we have to deal with. So we have a 3-member timber connection, a bolted connection between vertical member and 2 side horizontal members, 10 millimeter bolts, 8 diameter end distance in the vertical member, and the row spacing and bolt spacing is 5D. So in this case, 50 millimeters. The bolts would be located at the center of our center height of our side members. And in this case, we would need to just look at the joint resistance. So just one step in the design. So each of our horizontal pieces taking half the load applied to the vertical member. So we would have a force of P over 2 on each faces of our vertical member and on the vertical face, the inside vertical face of our side members. In terms of possible scenarios, both of our vertical and side members could be subjected to ductile failures, where we have compression parallel to grain in the vertical one and compression perpendicular to grain in the side one. But we also have brittle failures, and these brittle failures are different in our vertical and side members. So we have net tension, groove tear out, and row shear in our vertical member, and splitting in our side horizontal member. So the design would take care, we would first look at the ductile failures, because that will determine the number of bolts. So getting the embedment in the side members for F1, and getting the embedment F2 for our main member. Once we have these 2 values, we get our beta value and our M sub Y for our 10 millimeter diameter bolts. Using these embedment values, our thicknesses, and our beta and M sub Y value, we're now in a position to get the different resistance for our failure modes. So if we get crushing in the side members only, we would end up with 6.1 kilonewton per bolt per shear plane. If we get crushing or embedment failure in the middle member, our T2 member, then we get 7.8 kilonewton per bolt per shear plane. If we get the development of 2 plastic hinges in our fasteners and combined with some crushing in our timber members, we get the left term of the EYM equation. We get 2.9, and then we get this NAX over 4, which is our rope effect, and this is either the minimum of the tensile resistance of our 10 millimeter bolt, or crushing under the washer, or the value of our left turn, which is the 2.9 that we obtained from these formulas. That's the one that governs, and for this case, our resistance would be 3.6 kilonewton per bolt per shear plane. The next equation is the one where we have formation of 4 plastic hinges. So we evaluate the left term again. We get our 3.15 kilonewton for that portion, and again get our rope effect evaluation. And in this case, again, it's the 3.5. That's the left term that value that governs, and we get 3.9 for the resistance of that case. So it's the equation C, a resistance that governs our ductile failure mode, and we plug this into our overall connection design. We have our 6 fasteners and we have our 2 shear planes. So for this case, our ductile resistance is 43.2. And this is a case where we have formation of 2 plastic hinges. So we don't know at this point if the plastic hinges is in the side members or the middle member. We move on to the ductile failure, the brittle failure, and we look at the vertical one first. We have row shear. In this case, we know that the end distance is 8D, so 80 millimeters, and the spacing of the rows and spacing of the bolts in the rows is 50. So we end up with a row shear resistance per row for one row of 77 kilonewton. And we, for the 2 rows, we would need to multiply this value times our 5 factor of material reduction factor of 0.7, our load duration factor of 0.8, and our service condition factor of 1. So our row shear resistance for the 2 rows is 86.2. The next brittle failure mode is the group tear out, and we use the value for our row shear of 1 row at 77 kilonewton. We look at the critical area between the outer 2 rows, and that gives us 3,420 square millimeters. So our 77 is for 1 row. We have 2 rows, but we need to multiply by 0.5 or divide by 2 because our row shear value of 77 is for 2 shear planes per row. And our group tear out only has 1 shear plane per outer rows. The tensile component is given by the right terms, and we end up at 102.6 kilonewton specified, and we need to multiply by our material reduction factor of 0.7 for brittle failures, our load duration, and our service condition, and we end up with 57.5 kilonewton for that mode of failure. The last one is our net tension resistance. This is an equation that was already in 3603, NZS 3603. So it's just a matter of getting the net area at the critical cross section. And we have 10,440 square millimeter. Our tensile resistance for this MSG8 is 6 MPa. So our net tension resistance is our material reduction factor for that equation is 0.8, even though it's a brittle failure. We have the 0.8 to the right for our load duration and our 1 as our service condition. And we obtain 40.1 kilonewton for that mode of failure. The last brittle failure mode that we need to look at is the splitting resistance in the side members. And the resistance for splitting is given by this equation. It's based on fracture mechanics. There's a portion of tension perp to grain, and there's a portion of shear parallel to grain in the equation. The definitions of the different DE values is the distance from the bottom fastener to the top of the member, because the splitting will occur at the bottom. The top of the side member is being pulled up. The D is our 240 millimeter, and then because there's a certain distance here, we have our 170, which is our D sub E value. The A sub R is the distance between the horizontal distance between our column of fasteners. So we obtain a G1 norm and G2 norms, and we have from our material our G1C and our G2C. The K sub R is a factor that takes into account the number of rows in our connection. So because that splitting force is divided per the rows of fasteners, so we actually increase our splitting resistance if we have more rows. So for one side member, our resistance is 0.6 times the 70 times our K sub R and divided by our two terms, and we get 30 kilonewton for the non-factored resistance, non-factored splitting resistance. If we want the design value, we need to multiply by our material reduction factor of 0.7 by the number of sides. So we have our two members, two horizontal members, and our load duration at 0.8 and our service condition factor of 1. And we obtain for our splitting resistance for the side member of 33.6. So for this type of connection, there's the splitting of the side members would govern. So in this case, the load path is quite simple. It goes from the vertical to the side member through the bolts, and really the different failures in both the vertical and the side members take into account the resistance of the connection. Example 3, it shouldn't be example 4, it should be example 3. It's a bottom truss connection, and in this case, there's a mixture of timber connection failures and steel design. So we have a truss, it's a 15-meter span, there's 1 meter overhangs, the slope of the roof is 30 degrees, and the members are LVL 13. It's the connection at the bottom is steel, wood, steel, bolted connection. So we have compression forces of 202 kilonewton in our truss top cord, 175 in tension in our bottom cord, and we have a vertical reaction of 101 resulting from the 202 and 175 forces, and the 13.5 coming from the overhang. And this 13.5 will need to be resisted in a different way. So to look at the connection free body diagram, we need to understand or need a bit more information. And this information is how this vertical reaction is actually transmitted to the support. Well, one possibility is to have a vertical component, to have a, extra support that is attached to the connection side plate. And that extra support would take care of the vertical component at the connection. So if we have this, then the bolts will do all the work, and the top cord connection will be designed for compression force only, and the bottom cord will be designed for tension force only. The second possibility is if the vertical component is transferred to the support at the underside of the top cord. So in this case, then the top cord would be subjected to compression parallel and compression perpendicular, and the Atkinson formula would need to be used to get the bolt embedment strength at this point. It's just a bit more complication in the design of the bolted connection in the top cord, but nothing is overwhelmingly complicated. For the steel plate, the bearing would need to be checked at the bolts. The row shear and groove tear out would also need to be checked in the left end of the plate, and the top cord bolts would have a different failure shear plane in this case. For the timber members, the bottom cord would need to be checked for ductile and brittle failures. So we would need to check the EYM, the row shear, the groove tear out, and the net tension, as we saw in the example 2. One thing that would need to be looked at in more detail is the row shear resistance, as the top row would have a shorter end distance, then the top row end distance would be the one governing the resistance, the row shear resistance of that connection. The top cord would need to be checked for ductile failures only, so only the EYM. So there is compression in that member, and there's so for that loading case, so no brittle failures in the top cord. Example 4, I think we have time, and this one is a hidden connection between glulam members, and this one is a mixture of timber behavior, connection behavior, and steel design. It's a practical example. It's the Credit Valley Hospital atrium in near Toronto. The structure was designed by architect Ty Farrow, who specializes in having timber, using timber in hospital. The concept was to mimic entering a forest. So, and then in this case, the glulam the curved glulam members would represent the trunks, and the side glulam members would be branches that support the roof members. One of the requirement was that the steel was to be non-visible, so a challenge, but a nice challenge for a timber engineer, really. The steel brackets are all concealed within the glulam members. Tight-fitting dowels were used extensively. So I will go through some of the design, but you can see the bracketry, the steel bracketry installed in the side of the curved glulam members, and some peculiar holes in those members. Load paths and the checks that are required. Well, the tree branches, if we start with gravity loads, the tree branches gravity load would need to be resisted by dowels with steel knife plates. So the connections would be designed assuming ductile failures only, as it is compression. The knife plates would need to be designed as cantilever columns. So one would need to verify plate buckling. So we see here the forces are coming at a certain angle. The plates reflect the angle of the branches, the glulam branches. The sequence of installation was very important in order to be able to insert those tight-fitting dowels, and the compression transferred from the member to the dowels to the steel plate would be designed using the EYM, the European yield model in this case. The plates were designed to avoid buckling. The next load path and checks required were the welds between the knife plates and the back plates. So welds and shear. The back plates needed to be designed to transfer the gravity forces to inserted steel hollow section into the tree trunk. So shear in the weld between the back plate and a bearing block. I'll show this later. And then the bearing block would need to transfer the force to the inserted SHS in bearing. So cross section of the curved glulam beam. We see here on the right the weldments with the plates connected to the branches. The back plate is vertical, and in the back plate there is a bearing block that will provide the reaction to the vertical component of the branches. And then on the left side of the cross section, we see the back plate inserted into the SHS. We see to the photo on the left, you can guess this block that is at the back of the back plate, and if you want to see the inserted hole, well, we see them here. We see one in the glulam curved glulam member, right, and we see these bracketry that are in place on the curved glulam member to the left. One can also note the treaded rods and another inserted SHS in the member here as well. So the back plate was secured with the treaded rods, and we can see also plate at the top of the member. So the back plate has a steel block welded to it, and it fits within the SHS to transfer the shear. So that's goes at an angle with the branches, vertical component transferred through the bearing block, and then the SHS is working as a beam. So we have the SHS in bending, and we have the bearing block pushing down, and then we had threaded rod connecting the inside of the SHS to the steel plate at the top. So we needed to make sure that the SHS was of the right size, right thickness to be able to resist this bending without significant deformation. Deformations was very critical. The entire strategy to go this way was to have a concealed connection that would prevent splitting in the arch glulam member. And then the last checks or last load path and the checks required were to design the treaded rods, so making sure that they were the right diameter, the right grade, and then the bearing plate at the top. So bending of the plate needed to be checked to determine its thickness, and its length was determined by sizing it in terms of its length. The width of the plate was the entire width of the glulam member. So you have an installed connection at this point. So this is more or less what was involved in designing each of these connections. So a lot more involved, but very interesting to do. And that was the final cross section. Everything looked very nicely in that structure at the end, and it's really a nice case study to show. So, to conclude and summarize, one needs to know the weaknesses and strength of timber. Weaknesses, compression perp to grain, tension perp to grain, really. Free body diagrams, I repeat this, they are a must at each design steps in order to explain the design strategy. And really the important thing, tell the students to follow the load path from one member to the next and through all the different components and through all the different loading actions. Thank you for your attention. Hopefully we'll have time for questions. Thank you.
Thank you, Pierre. We do have a few questions, and we've got about 15 minutes for those. I'll start with the most upvoted questions. First one from John Tate. Have there been any recent updates with regard to errata and updating of the new standard NZS 1720? And do you have any sense of a time frame for this being cited in the building code?
Not sure at this point where the errata has it's at. I think the Timber Design Society members are working on this. Probably the question would be better asked to the Timber Design Society for that to get a better answer on this one.
Okay, thank you.
Yeah.
Next one. So during design, engineers often struggle with meeting the timber edge distance requirements per 3603.
Yes.
The examples that some Bomac brackets don't permit 3603 tension along grain edge distances. Have you got any comments about how stringent or practical the edge distance requirements are and what engineers can do when dealing with limited edge distance?
Yes, yeah. The edge distance is mostly because one wants to avoid splitting, and if there is potential for shrinkage in the member, uh, if the fasteners are too close to the edge, then there is potential for splitting. One way to overcome this is to reinforce the edges by putting transverse fasteners, and it doesn't take much. If one is stuck where by the connection dictating the size of the member, which is really uh, not a good outcome, and the edge distance is that the culprit, I would consider reinforcing transversely the edges with transverse connectors, transverse fasteners.
Thank you. All right, next one, Nick Calvert. Find that the complex thing about equations isn't just chugging and plugging into the formula, but selecting the correct values for different variables. He's wondering if there could be a part 2 of the presentation on how to select the variables that go into the equation. I don't know if you're able to answer this one now. Maybe we could look to a follow-up.
It's up to you, Jenny, but I'm always ready to provide more explanation. That's not a problem. Yeah.
Do you have any commentary on that? Is that something that you see a lot of people struggle with in practice?
I think it's just to do with going through the examples. There's been some presentations by True TDS, Timber Design Society, and these presentations are available online as well. And there are some examples, and the more people see the examples, I guess the better the explanations are. But it's all about going through as many examples as possible.
Yeah, that's fair enough. Speaking of examples, and I think we're going back to the first example here. The question is, wouldn't the dowels connecting the glulam beam to the steel plate transfer load into the steel plate web so the bottom flange isn't taking all the load?
Yes, that's a good question. In this case, these dowels were very small, so they were just to make sure that the dowels, that the steel bracket was connected or remained in place during installation. It was really nominal. So to make sure that the dowels take the load, they would need to have a certain stiffness, and one would need to make sure that it's a stiffness issue. What is the stiffness of the dowels of a certain diameter in bending in comparison to the stiffness of the timber itself? But it is a check. It is a check that one would need to make sure that the dowels are flexible enough in terms of so to not take the load. Yeah.
Right. Okay. Next question is in relation to example 2. And it's so it's about the equations themselves, just noting that I guess with all the equations, it lends itself to resolving through a spreadsheet. I guess especially if you need to go through a bit of an iterative design process. Just wondering if there are any central resources you're aware of for sort of design spreadsheets that might be able to help, or if individual firms
Yes,
just need to build up their own library.
Yeah, I think actually, I've been working on this for quite some time. I'd be willing to share spreadsheets. That's not a problem. Just send me an email. Yeah. Obviously, spreadsheets will come with the, statement that I'm not responsible for its use, but the spreadsheets have been developed and used in class and vetoed with students over a number of years. Yeah.
Cool. This next question, I think it's about example 4. Just wondering, what's the construction sequence for the tight-fitting dowels, and considering construction tolerance, are the holes in the timber site drilled? And if so, how does the contractor get them in the right location?
Yeah, that's a good question because this project was done before CNC was used extensively um, in the design and in the fabrication. So, like this project was done in the early 2000s. It was all AutoCAD 3D. I actually probably AutoCAD 2D at that point. A lot of trigonometry calculation. I cannot say that there weren't any misalignment of dowels. I am not aware. I've never been reached out to by the site manager saying that it did not fit. It's a matter of quality control. We were very sure of the steel bracketry, that's for sure. There was a lot of quality control in the steel, but a 1 or 2 millimeter misalignment in a tight fitting dowel is never an easy one to work with, and there's a lot of, sometimes even these dowels were 20 millimeter in diameter, so sometimes I've seen a lot of pounding of a dowel using sledgehammers. Yeah.
Sounds like a fun one to build.
Well, yeah. Yes, but the erection sequence on this one was important.
So you talked a bit before about trigonometry. So I'll jump to this question. It seems like a lot of calculations and design effort for even the most basic timber connections, particularly for smaller projects. Is there not some simple requirements that can be provided for the connections to be robust?
Well, definitely the easiest is to transfer forces through bearing. That's probably the easiest one. But it all depends on the requirements, the architectural requirements. Yes, I was involved in projects where a lot of repetition was the norm, and at that point, for these types of projects, we would develop spreadsheets and come up with very fast connection design for these repetitive connections. But an engineer, as an engineer, I really relished in the design of connections shown in example 4 because it was really interesting. And this project, a lot of connections had more or less the same same configuration, but because the snow load was on the atrium was not symmetrical, a lot of the forces were different for for the same configuration. So very, very time consuming, but it's a project that was very interesting.
Mm. Okay. So another one about example 4. So in the example, the bolts are connected to hold the SHS in place inside the member. Does this need specific embedment? And if so, how do you determine the embedment?
So the embedment of the, I'm not sure I understood it. The embedment of the tight fitting dowels in the branches, was that the question?
I think
Or is it the threaded rods?
I think it's the threaded rods.
Okay, so the horizontal threaded rod was just to keep the side brackets in place. So that was because the gravity load was such that it was pushing the brackets to the side of the curved glulam members. So there would never be any chance of the brackets being pulled out. But for erection, we needed to have the threaded rod installed. The vertical or the inclined threaded rods that connected the SHS to the top plate had to have the right diameter, and the SHS had to be of a certain size to allow the hand of a worker to install the nut in the washer, the plate washer, and the nut in the SHS. So that was one of the considerations that we needed to take into account. Yeah, I don't know if it answers the question, but that's the
fingers crossed.
yeah.
Okay, we'll just do one more question. So for the first connection, what prevented the rotation of the bracket given the relative eccentricity of the top and bottom plates?
Yeah, the one I'm sure that one as notice the 4 tight fitting dowels at mid height of the member, and again it's a matter of how flimsy or how flexible these tight fitting dowels are in relation to the deformation of the beam under gravity load. So it's a type of bracket that is used a lot in terms of transferring vertical forces because it's true bearing and tension in steel, and so it's fairly robust in terms of a bracket. But the overhang of the supporting beam will have a negative curvature, and the simply supported beam will have a positive curvature. So there is somewhat of an alignment of the bracket, and so that's why they say it's not so much of it's transferring vertical force, but not transferring much moment, if any.
Okay, thank you. We are now at 1 o'clock, so just want to say again, thank you so much for your presentation. I'm sure everyone has learned a lot. I clocked almost 400 participants at one stage, which is really exciting.
Okay.
Yeah, so thanks.
Okay, thank you.